Dear students, welcome to the online classes for acoustics. In this lecture, we will be talking about the design considerations for speech. This is as per your syllabus. This is given in module 1, which is about the design principles and factors. So, first of all, we will be talking about the design principles, the basic requirements for speech, and then we will take examples of the spaces for speech, that is classrooms, conference rooms and boardrooms. First, the objectives of this lecture are the first point, that is the fundamental requirements in designing rooms for speech. So as an architect, we have to design, we have to give the shape and the size of the room as per the capacity of the room, anthro and standards. Then comes the second point, that is design considerations for speech. In the last lecture which I have taken in the classroom, this has been told to you that for any kind of space where speech is of prime importance, the speech intelligibility is the main criteria. Speech intelligibility means the clarity of sound, how much clear the sound we are receiving. So in the third point, we will be discussing about the acoustical criteria and the space design for various spaces where speech is of prime importance, that is classrooms, conference rooms and boardrooms. So this is the referred books, that is Concepts in Architectural Acoustics by M. David Egan. These are the fundamental requirements in designing rooms for speech, which are given by Dole, a professor in environmental acoustics in 1972. The first point is there must be adequate loudness, that is the direct field level should be high, that is source sound pressure level should be high, especially in the case of small rooms because of the unreinforced sound. The direct level should be loud enough, the source sound pressure level should be high enough. The second point, the sound level must be relatively uniform, that is the sound does not create any kind of jerk while receiving by us. Then the next point, the reverberation characteristics of the room must be appropriate. In the last lecture, we have used technical terms such as dead rooms, live rooms and medium live rooms, and we have shown you a chart in which these rooms, dead room, live room and medium live room, are being plotted with respect to the volume of the room. So we can find it out, the reverberation time, from the chart, or we can get it from the NBC. So we have to take care of the reverberation time that is required for a particular space. Then the fourth point, there must be high signal to noise ratio. The signal, the sound source pressure level should be high in comparison to the background noise level. That is, the difference value is not going to affect the signal sound pressure level. Then background noise level must be low enough so as to not interfere with the listening environment, and the room must be free from acoustical defects. We have talked about it, long delayed reflection, that is the late reflections, flutter echoes, focusing and resonance. Due to resonance, standing modes develop, room modes develop. So we have to take care all these kind of acoustical defects that may occur in a room. And beyond 30 to 40 feet, it is difficult to understand unreinforced speech. Unreinforced speech doesn't mean we are talking about reflected sound. Unreinforced and reinforced speech means, reinforcement means we are using some kind of electrical instruments to reinforce our speech. So any kind of microphones, any kind of mics we are using, that is basically we are reinforcing the speech. Optimum volume per seat should be 110 cubic feet, that is 3.1 cubic meter. The normal range, the standard as per the standard for classroom is 80 to 150 cubic feet. And if the volume of the room is less, then the loudness will be more. And as we know, RT is equal to 0.16 V upon S alpha, that is absorption. So if the V is going to be decreased, we will get the RT in a lower value. Children, especially primary section, 100% intelligibility is desired. Why 100%? 100% because a student of a primary section does not have any perception. So any kind of word, if we say any word and small proportion has been told, so what word next is going to come, he would not be able to make it. As in the case of an adult person, if we say any word in reference to context, he or she would gather what we are going to say. So a small child doesn't have any perception, and if we say any one word, his brain would not know what could be the rest part. So 100% intelligibility is desired, but 80 to 90% is also good enough. The second point, children should also be heard to the teacher. The noise level, background noise level should be low enough and reverberation time should be low. Both is desired in the case of classroom design. Additional aid for the students with hearing or language disability. So any kind of disability in terms of hearing or language, so we have to give additional aid to the students. And the sources of noise like HVAC ducts, wastewater lines, any fan humming, these are all the background noise sources which are also of low frequency sound. So we have to avoid those background source noise level in terms of acoustical design considerations of classroom. We already know about the inverse square law, that is pressure reduces with the increased distance. The sound source pressure level decreases by 6 dB for every doubling of the distance. So as you can see, if we move from 3 feet to 6 feet, the sound source pressure level from 15 dB, it goes down to 15 minus 6, 9 dB. So for every doubling of the distance, the sound pressure decreases. And as you move ahead, we can see at about 24 feet, we are getting the sound source pressure level as minus 3 dB. So how a student is going to know about or get the clear sound from the teacher? So in this case, the direct sound energy is not received by him. So in this case, the reflected sound is going to supersede. So the reflected, he will be getting the most of the sound by the reflected sound. The first chart, we can see this blue dotted line which depicts the direct signal and this green line as the early reflections. Now by definition, the critical distance is the meeting point of early reflected sound and the direct signal source sound pressure level. So that is the meeting point of the two, and after this critical distance, as you can see in the figure, the direct field decays significantly, and whatever signal we are receiving after the critical distance, is from the reflected sound, the early reflected sound. In the second chart, where you can see these are the different reverberation times given, which are color coded. So, as we know in speech, we require a reverberation time of about 0.4 second to 0.6 second. So, by knowing the reverberation time and the volume of the room in which we are designing, we can know the critical distance. So in the slide, this vertical axis is given the critical distance and horizontal axis is the volume of the room. So by considering the RT which is required in a particular room, which is desired in a particular room, we can get the critical distance from this chart. So as you can see in this slide, there is a plan of the classroom where there is an orderly arrangement of the sitting is there, and you can see in the plan itself at the end, at the back side of the speaker or the teacher, there is a reflector, and there are absorbers on the side walls and at the back wall. So for any kind of small classroom, these phenomena generally occur for a flat floor where there is no slope, where there is no raking, or there is no higher platform is given. So there comes a word called as grazing attenuation. We get this word from the basic phenomena that cattle rearing in a field, so they are basically grazing in the field. So that grazing attenuation means when the sound source is incident at a very shallow angle, at a very low angle, so there will be the sound will be attenuated to somewhat extent. So grazing attenuation generally occurs when there is no slope and when the sound source is incident at a very shallow angle. We will be describing in detail in the next slide. Now the critical distance, as we have already discussed, is the distance at which the source sound pressure is equal to the reflected sound pressure. And then the direct source sound decays and we are receiving the signals through the reflected sound. The critical distance, as we have seen in the chart, it depends on the volume of the room and the reverberation time. Beneficial reflections, preferably from the overhead, should be designed. Why so? Because we are getting uninterrupted surface on the ceiling. And in a classroom, on the side walls, maybe we have some kind of panels or soft boards or some door or window. So on walls we are having interrupted surfaces. So in order to achieve a high early reflected sound, we can use the ceiling part. So the beneficial reflection should be taken from the overhead. And as we know, the frequency of the human voice is about 500 Hz to 4000 Hz. So at the back end of the classroom and at this side wall, as you can see, the absorbing panels are porous in nature. So from 500 Hz to 4000 Hz for high frequency, the porous absorbers are the best absorbers for absorbing any sound. In this, one of the side walls is for the absorbing panels for the low frequency sound. I have already told you the low frequency sounds are basically the background noises. Maybe some kind of pipe water going from the pipes which are adjacent to this classroom, or maybe some kind of HVAC noise, or maybe some kind of fan noise. So for those noises, we have to give absorbing panels for specific low frequency sound also. Grazing attenuation is a phenomena that occurs when an acoustical wave interacts with an absorbing surface at a very shallow angle of incidence. For example, if we have any carpet on the floor and the sound source incidence angle is very shallow, that is less than 5 degree, then a lot of sound will get attenuated. And this phenomena is usually seen outdoors when there is grass or snow. You can see in the figure, this is the height of the source, then there is a long room. The length is very long, the 30 times the height of the source, then we are reaching the middle portion, and then again 30 times the height of the receiver. Then we are getting to this height of the receiver. As you can see, the blue line is the direct path and the red line shows the reflected path. And when this reflected path, if we can see, the theta is the angle, and in this figure we are getting the theta less than equal to 5.8 degree. So for very shallow angles, for the incidence rays which are coming at very shallow angles less than 5 degree, the grazing attenuation will be there. The sound will be attenuated, and it is going to be this phenomena is going to be controlled in auditoriums by raising the talker height, by raising some kind of platform for the source, or by sloping the floor, that is raking the floor. The design details in terms of classrooms. As you can see, this is the talker, the speaker, and there is a high platform of about 1 feet. So even by raising the platform of 1 feet, we can decrease the grazing attenuation. So grazing attenuation will be controlled by raising the talker, in which the angle of incidence will be greater than 5 degree, and this kind of raising the platform also increases or improves the sight lines of the viewer. And as you can see, the speaker, at the back of the speaker you can see the back end of the wall, there are reflectors, and above the speaker you can also see that there are reflectors. So never use any kind of absorptive material near the speaker. The sound source, the direct sound source, has to be reinforced from the reflected sound. So this is best possible by giving reflectors around the speaker so that source sound is reinforced. And then at the ceiling level, you can see there is a false ceiling, drop down level, and the ceilings have been treated with porous absorbers to absorb high frequency sound. Then in a large flat floored classroom, a platform of 1 feet height can improve the sight lines also. The RT is a function of height. So RT is equal to H, height of the ceiling, in feet divided by 20 alpha. So if we know the height of the ceiling, or we are suggesting some kind of down ceiling, so we know the height of the ceiling and the RT required in a classroom, so we can figure it out that what should be the absorption coefficient of that porous absorber. So from this calculation, typical classroom sizes of 8 meter by 10 meter generally accommodates 30 to 40 students, and ceilings in classroom should be low enough to add to the early reflections. That means if we are dropping down the ceilings, we are basically reducing the volume of the room. Low frequency sound, that is any kind of background noise level, is of no importance in speech, and hence appropriate absorbers must be added to reduce the low frequency sound. Reverberation times preferred in a classroom is between zero point 0.4 to zero point 0.8 seconds. Intelligibility, which we have already discussed about the clarity of sound, that should be maximum. That means at least 80% of the words of the syllable should be clearly heard by the listeners. Then it comes under speech intelligibility. Reflective surfaces, surfaces near the source should not be covered and it should be reflective in nature. There shouldn't be any absorptive surfaces near the source.